my greatest honor to introduce Steve Awodey, our second keynote speaker. Stephen is a professor of philosophy and mathematics at Carnegie Mellon University. Currently, Steve is a Royal Society Watson Visiting Fellow at the University of Cambridge.
That's right.
Steve is one of the originators of the field of Homotopy Type Theory.
Yes.
Today, we're talking about what it is.
Okay, great. Thank you, Tianzi, for that introduction and for inviting me to this meeting, this workshop, and thank you, Pietro, for having me here. It's a pleasure to be here and to learn about what's happening in your field. This is not my field. My field is Foundations of Mathematics, and from there I've moved into formal theorem proving, and I'm interested in learning about connections between automated theorem proving and AI, and so that's why I'm happy to be at this conference to learn something from you. And now I'm going to tell you something about what I do, which may or may not be relevant to your interests. So we'll give it a try. So homotopy type theory is a field of foundations of mathematics, recently discovered maybe last 15 years or so, with applications to formal computational proof assistance and theorem proving. It's based on a system of type theory, which I'll tell you about in a minute, which has an unexpected interpretation into homotopy theory. Homotopy theory is the mathematics of continuous deformations of space, functions and spaces. The system extends an existing system called Martin-Löff's constructive type theory. I heard Martin-Löff's name come up earlier. He not only worked in statistics, which is maybe where you're familiar with Martin-Löff, but also in the foundations of mathematics and in constructive mathematics. And the system extends Martin-Löff's constructive type theory with new principles to strengthen the connection to homotopy theory. Now, maybe by coincidence, Martin-Löff's type theory is also used in computational proof assistance theorem provers that are currently experiencing a burst of development. There's the lean system, which you may have heard of. That's the most popular one right now. There's also ROC and AGDA and others. These things are used in computer systems for proving theorems, and Martin-Löff type theory underlies these systems. Now, because of that, and because of the connection to homotopy theory, that means that Martin-Löff type theory can be used to formalize and automatically verify proofs in higher mathematics, like in homotopy theory or higher category theory. And but there is a hitch or a question, and that's going to be kind of the leitmotif, if you will, of the talk. Martin-Löff type theory was originally developed as a constructive system of foundations, and it has a constructive character, which allows program extraction, some amount of automated reasoning, and inference of values, computation from proofs. The interpretation into homotopy theory adds some new features, and the question is, do those new features preserve the constructive character of the type theory, or do they destroy the constructive character? So that's the kind of rhetorical question that I'm asking, and that's what the talk is kind of centered on. So type theory. Type theory goes back to, so extra points for anyone who can name all four type theorists in this rogues gallery of type theory. Anyone want to give it a try? Here's young Frege. Here's our hometown favorite, Bertrand Russell, as a youngster. Kurt Gödel, and here's our current hero, Per Martin-Löff. So the constructive type theory of Per Martin-Löff has a curious feature. It replaces logical formulas and their proofs by types and their terms. So the slogan maybe is propositions as types, proofs as terms. So the types, the basic underlying types in the type theory, may be something like the natural numbers, and then you can build some new types out of existing types by taking the product, the sum, or the function space. Each of the types has terms. The terms of a type you think of maybe as like elements of a set, but there's an additional twist. The unit type has a single element. The natural numbers type has natural numbers as elements. The product type has pairs and so on. Here's the distinctive feature of the type theory is this lambda abstraction, which takes a term of type B involving a variable of type A and produces a function, which is written with the lambda abstraction. You probably have seen this before, which denotes the function which takes the argument x to the value b of x. Now, a special feature of the Martin-Löf type theory is that it has also dependent types and terms. I'm just going to tell you briefly about that. A dependent family of types parameterized by a variable in a type is thought of as a varying type, which varies in that parameter, and then a family of terms, also varying in that parameter, represents a family of terms of those varying types. And once we have such a notion of a variation of types in a parameter, we can build new types, which may be the sum or the product of all of the types in the family. So that's the idea here. I'm not going to teach you very much type theory here, but I want you to get a sense of how these operations work, because there is a curious phenomenon happening here, and that is that these operations, sigma and pi, are acting kind of like the quantifiers in a logical system, the existential and universal quantifier in the system. So for example, if I have a term of this compound type, where this is some relation between x and y, and then the compound type says pi of x, sigma of y, rxy, such a term determines a computable function from the a's to the b's. And it determines it as follows. I can evaluate it at some a, and I evaluate that term, and I get some cross-section of this family, and then I can project it out, and then I get an element at a of the type b, which is T1 of a, and that is a function from the a's to the b's, and you can in fact show, or it has been shown, that this is a computable function. So a term of this complex type automatically determines a computable function which can be extracted from a proof of this type. The terms, again, are proofs. The types are propositions. And this corresponds to the proposition which says for all x, there exists a y such that rxy. So if you are a logician, you'll recognize that as the axiom of choice. So a curious feature of this system is that you can prove the axiom of choice constructively in the system. And in fact, the axiom of choice says if for all x there is a y, blah, 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 then there's a function that returns the y's from the x's. And the function here is just the term that you've used to prove the for all x there is a y. So that's the idea. You can extract automatically functions, computable functions, from proofs. So that's the kind of basic idea that makes this system of interest for maybe computational proof systems. The constructive character of the type theory gives rise to this idea of automatic program extraction. Okay, so I already have kind of shown you or suggested how we replace the familiar logical operations by these type theoretic operations. Here's the universal quantifier for all x, turns into this product. The existential quantifier turns into a sum, and the function type is coming from the implication and so on. Of course, as you remember from your elementary logic that you learned in high school, this is not all there is to logic. There's one more essential feature in logic, and that is the identity relation, which is kind of one of the basic relations from which you get going. And that was a contribution of Martin-Löf, was to introduce a new type which represents the identity relation. But of course, in type theory, the types are more than just simple propositions, yes or no. They have structure. They can have many different terms. They can give rise to further operations. And once you introduce this identity type, you get the possibility of lots of different terms of identity type which correspond to different proofs of equalities. And that made a kind of mysterious character in the system. What does it mean to have different proofs that A equals B? There's a kind of undetermined, or at least unfamiliar situation going on here, because if we have two different proofs that A implies B, well, then we can interpret them as two different functions from A to B. That's no problem. But what does it mean to have two different proofs that A equals B? And that was a kind of mysterious character in the system, and the solution is this. So it took a while to come up with this idea. The idea is we take Dana Scott's topological interpretation of the lambda calculus, which you may have or may not have seen before, where the types are interpreted as spaces and the terms are interpreted as continuous functions. This is Scott's idea that computability is modeled by continuity. We take continuous functions, and now we extend that interpretation by one step. We say a proof that A equals B corresponds to a continuous path between the points A and B in the space X. So that's the fundamental idea of the homotopical interpretation. If the type X is a space and the terms A and B of type X are points in the space, then a proof that A is equal to B is a continuous path from A to B in the space X. So that's the idea. Continuous path is, of course, just a continuous function from the unit interval. And now if we extend that interpretation to all of the type theory, it propagates through the dependent types, the sigma, the pi, and so on, and it gives us the entire theory admits this interpretation of the identity types as continuous paths, and that gives rise to a homotopy or homotopical interpretation of the whole type theory. So I'm going to tell you a little bit about that. I would draw a picture if I had a board, but you imagine a space and 2 points and a continuous path from one to the other. That's P going from A to B. Imagine I have some Q going from A to B as well. Now I have 2 continuous paths. What should be a proof that P is equal to Q? Well, it's a continuous deformation of the path P into the path Q. It's a homotopy from P to Q. And that's where the homotopical interpretation starts, and that's how it works. So, in fact, the relation of having a continuous path satisfies the usual laws of identity. I'm just kind of rehearsing now the fact that the interpretation makes sense. The usual laws of identity are reflexivity, symmetry, and transitivity. If I have a path from A to B, then I must have a path back from B to A. It's the same path traversed backwards. If I have a path from A to B and a path from B to C, I can traverse the 2 paths and I get a path from A to C. So those are the usual laws of identity. But of course, there are higher laws of identity. There's the associativity, for example, and other laws, like if I reverse, then the round trip across and back should be equal to just staying put at A. And that's one of the laws of homotopy theory, that I can deform going out and back to staying at the point. So these paths satisfy higher laws given by homotopies. And in fact, one can prove that in the Martin-Löf type theory, every type is endowed with a higher structure, this tower of identity types at higher and higher levels, that by higher I mean higher dimensional, paths, paths between paths, paths between paths between paths, and so on, which are interpreted by homotopies. And what we get is, inside the type theory, every type is endowed with the structure of what's called an infinity groupoid. It's a category in which every arrow is invertible, and in which there are arrows between arrows and arrows between arrows between arrows, and so on. Infinitely many dimensions of such categorical structure. This notion of an infinity groupoid comes up in the type theory. One can show in Martin-Löf constructive type theory that every type bears the structure of an infinity groupoid. Now that's an amazing fact. We didn't invent infinity groupoids. Grothendieck invented infinity groupoids. Grothendieck is, I'm sure you've heard the name, maybe the most prolific, famous mathematician of the 20th century. And one of the things he did was he invented infinity groupoids, and he proposed a conjecture that infinity groupoids can be used to classify homotopy types of spaces. These are maybe equivalence classes of equivalence classes of topological spaces under homotopy equivalence, deformation of one space into another continuously without tearing it. And these things are classified by infinity groupoids. So here's a very powerful connection, or suggestive at least, between, on the one hand, the constructive type theory, where these infinity groupoids just popped up without us doing anything. We discovered that they're in there. We didn't put anything new into the type theory. And on the other hand, infinity groupoids, which are a kind of higher dimensional, infinite dimensional algebraic structure from category theory, and now homotopy theory from topology and continuous deformations of spaces. So when a coincidence like that happens, it's very exciting, and one wants to pursue the underlying mathematics and then try to transfer ideas back and forth along this bridge or coincidence between homotopy theory, category theory, higher category theory, and constructive type theory in the foundations of mathematics. And that's exactly the program that then we started pursuing. And now I don't expect you to understand this slide, but I want to just mention this name, Voevodsky. When we started working on this project, it caught the eye of a famous homotopy theorist. I think I have a picture of him here somewhere. There he is, Vladimir Voevodsky. It caught the eye of Vladimir Voevodsky, Fields medalist and homotopy theorist, and he started collaborating with me and my students. And one of the ideas that he came up with, which was a very insightful and useful, was that the universe of all propositions is naturally stratified in the same way as the universe of all homotopy types. That's where the idea came from, is out of homotopy theory, by the level at which this infinity groupoid of identity types peters out. At some point it becomes degenerate. Like the natural numbers, there's no higher homotopy in the natural numbers. They're just discrete points, and that's the end of the story. Some types have higher homotopy. Some types have infinite dimensional homotopy. Some types don't have any discrete paths at all, like the Booleans. So you can write down in type theory, you can define this hierarchy of different levels, homotopy levels, Voevodsky called them. And it turns out the types are now structures, and that's a very useful insight which assists in reasoning about these types. So the universe of all mathematical objects, maybe you know from the set theorists, is stratified by size, higher and higher universes, bigger and bigger sets. That's a familiar idea. But now in type theory, what we realize is that stratification is only one dimension of a two-dimensional structure, and the other dimension, which is independent of size, is homotopical structure, where at the bottom you have the propositions, yes or no, no more data. Then the sets. You have a set, the discrete elements, and the discrete elements are either equal or not, yes or no. And then the next level, the groupoids, where you may have two elements and they may have many different equalities or identifications between them. But those may be equal or not, yes or no, and so on up. So you have all the different levels there. So that's a very insightful and useful idea. That's what was introduced by Voevodsky. There he is. And then, as a further insight, he proposed a new axiom in the foundations of mathematics, which you may not have heard of. It's called the univalence axiom. It has this pithy statement which says, if I have two types, then their identities, the type of identities between these two types, is equivalent to the type of equivalences between the two types. So that's a remarkable idea. It's very simple. It's kind of illuminating once you see it. What it says is that if you have, for example, two sets, equivalence for sets is just isomorphism of sets, being in a bijective correspondence. It tells you that two sets which are isomorphic or in bijective correspondence may be identified. Well, that sounds pretty good if you're a mathematician. You don't want to distinguish between isomorphic objects. You want to treat them as the same. And what Voevodsky's univalence axiom tells you is you can identify isomorphic objects, isomorphic structures. Isomorphic groups don't need to be distinguished as groups. They can be identified. And by can be, I mean you can put this axiom into the system of type theory and it will be formally consistent. And then you can reason with these identifications in a precise way that makes the system much more powerful, because now you have added this new kind of almost like a meta principle that tells you you've proven two groups are isomorphic, go ahead and identify them. It's fine. It's formally fine in the system, which the mathematician does every day anyway. In doing group theory, you identify isomorphic things without a second thought. But the foundations of mathematics don't usually allow you to do that. The foundations of mathematics would prevent you from formally identifying isomorphic things. So Voevodsky's principle says, go ahead, as long as you're working in type theory, it's okay to identify isomorphic things. Very powerful principle. But what about that constructive character that I told you about in the beginning? We haven't said anything about that. Doesn't that putting in new axioms, doesn't it spoil the constructivity of the system? So there was a conjecture at the time that, this is, I'm talking about 15 years ago, that this principle is still constructive, that it preserves the constructive character of the system. It's a deep and important conjecture, but it was far from obvious that this would be the case. So now I'm going to tell you a little bit about the solution to this and some test cases, and then finally how it worked out. I'll cut to the chase, though. The answer is yes, it's still constructive, but I'm going to tell you a little story about how we determined that. So one of the things that you can use the system for, now that it has this higher dimensional structure, and you can reason about the higher dimensional structure, is you can reason about things like the circle homotopically or a sphere homotopically. So a circle is just a point with a loop. That's a homotopical version of the circle S1, the one sphere. The point is a term of type S1. The loop is a term of the identity type of the base point. Okay? Because remember, loops or paths are just identity proofs. So S1, the unit circle, is generated inductively from a base point and a loop of its identity type. So once we have that, we can ask about what happens if we go around the loop twice? What happens if we go around the loop and then we go back again? It turns out those loops on a point in any space form a group, because of course you can go once, twice, and so on, and you can go back, and the loops compose. That's the group multiplication. And way back when, 1895, Poincaré introduced the fundamental group of a space. The fundamental group of a space, X, at a point, star, is all the loops from star to star in X, up to homotopy. That's the fundamental group of a space. It's a basic homotopical structure, an invariant of a space, and the topologists have studied these things for 100 and whatever years now. It's an important topic in homotopy theory. Now, we can import these homotopy groups of the spheres for all dimensions into homotopy type theory now. We can define them in the system of type theory, and we can try to compute them. So here's an example. Here's the fundamental group of the circle. Of course, it's what I just told you. So here's the type that it is. It's the identity proofs from the base point to the base point. And of course, informally or intuitively, you can see that must be the integers, right? There's the loop that doesn't go anywhere. There's the loop that goes around once this way and around again and again, and then going back and so on. That looks like the integers. In fact, that can be formalized we used here the Koch proof assistant, and you can calculate in the type theory and formally prove that the fundamental group of the unit circle is the integers. So this was the first calculation of one of the homotopy groups of the spheres in 2011. I'll tell you in a moment why and where that happened. And that was the initial breakthrough here in the kind of testing of this new idea by computing homotopy groups of spheres in the formal type theory and then automatically deriving the values of these homotopy invariants associated to the spheres. The topologists use the homotopy groups of the spheres as a kind of whetstone for their methods. It's a test for how to develop new methods and test the power of new methods to compute various homotopy groups of spheres. It turns out to be a very difficult problem. It's like the prime numbers are to number theory, the homotopy groups of the spheres are to homotopy theory, and there's a lot of research has been devoted to computing homotopy groups of spheres. So we took that as a target and started working on this problem. Now, one of the benefits of having attracted the attention of a big shot like Vladimir Voevodsky was he was a professor at the Institute for Advanced Study, and he organized and invited us to help organize a special year-long research program devoted to this topic. So we went to the Institute of Advanced Study. In Princeton, we spent a year. We invited 50 people, a lot of them my students and other collaborators, and we spent a year there at the Institute, sitting around in the tea room there with the laptops, using a proof assistant and computing homotopy groups of spheres, programming homotopy theory into this experimental system and testing this experimental idea of using computational proof assistants to compute homotopy groups of spheres. If you saw I'll tell you a quick joke. If you saw the movie Oppenheimer, there's a scene where he comes into the Institute, he goes through the tea room, he goes busting through these doors and going out to find Einstein by the pond to talk to him. I think they forgot to remove the bust of Einstein in that scene from the movie Oppenheimer. Anyway, so by the end of the special year, one of the participants, a very smart young student named Guillaume Brunery, proved in HoTT, in the formal system, that the fourth homotopy group of the 3-sphere, pi4 of S3, is Z mod n for some value n, but the value n could not be computed from the proof without having a system, a formal system that implements our type theory in a computer. Because part of what we were doing is we were doing these proofs on the chalkboard and on paper, and at the same time developing computational proof assistants that would implement the system. But at that point, we did not yet have a proof assistant, the proof assistant Coq. We were hacking it, but it didn't implement this proof. And so we couldn't compute the value of n, despite the fact that we had a constructive proof that there exists an n such that Z mod n is pi4 of S3. So here's Guillaume Brunery giving a lecture at the Institute for Advanced Study. You can Google this if you want to and watch this video. And here at 1:44:32, he points to the board and he says, so what we get is that pi4 of S3 is equal to Z mod n for this n. And this is one very concrete and non-trivial example of why we may want to have canonicity. That's the computational property that was conjectured by Voevodsky. Why we may want to have canonicity, because this n is a closed term of type Z, defined with a lot of univalence and higher inductive types. So in a perfect world, if you formalize that in a proof assistant with a computational interpretation of univalence, you can just ask, what's the value of n? And you'll get 2, because we knew what the answer is. Poincaré knew what the answer was. But the value of n, to automatically compute it from the proof, required a lot of machinery. So that's Brunery's perfect world, 2013. So what's that, 12, 13 years ago? What's happened since then? So here's what's happened. First, the constructivity of univalence was verified by Thierry Cocon, a computer scientist and logician, and his collaborators by developing a constructive version of homotopy type theory that does implement univalence and higher inductive types. So that took a few years. And then the next thing was to build a new proof assistant implementing this constructive system. That took another 5 years. And this new proof assistant is called cubical AGDA, and it computes with univalence and higher inductive types. So that was up to 2019. And then at that point, Guillaume Brunerie and other smart people started implementing Guillaume's proof in this new proof assistant. And it took many years, several years, before they finally had the entire proof formalized in this new system. And you hit return and you let it run. And it runs, and it runs, and it runs for days and days, and then it times out, and then your computer crashes, and then you go get a bigger computer, and then you go get a supercomputer, and you let that run, and that crashes, and it goes on, and you, at the same time, you try to improve the performance of the proof, and finally, in 2022, so almost 10 years after Guillaume's original chalkboard proof at the Institute for Advanced Study, it worked, and we weren't sure at this point, is there a bug in the proof? Is the proof correct? Is there a bug in the implementation? But finally, it worked, and it produced the value of 2. And that computation, the fact that the value is 2 is a little bit like, I'm reminded of the Russell-Whitehead thing, 1 + 1 = 2, which was the high point of Principia Mathematica on page whatever. Anyway, computed a value of 2. Since then, the proof has been improved. The time for this calculation is down to a few seconds now as we get better implementations of this thing and improve the performance. And the latest development in this now is just last month, an implementation in the same system, cubical AGDA, of what's called the Serre finiteness theorem. The Serre finiteness theorem is a proof that computes all the values of the kth homotopy group for the n sphere, pi k of Sn, for all k and n greater than 0. It's a single proof that computes all of the homotopy groups of all the spheres. So that's a landmark, a milestone, implemented in the Koch proof assistant. And in principle, what that means is you can put in a k and an n, and it'll return the presentation of the group that is finite, or at least a finite presentation of the group, which is pi k of Sn. Of course, we've tried to start implementing this proof. In fact, that has fully been formalized now in cubical AGDA, but it doesn't run, and it doesn't produce any values. So we're back to where we were 10 years ago with Guillaume's proof. We need to improve the performance, build better systems, but in principle, we should be able to automatically, from the proof, extract the term and compute the values of the proof. So that's the story. So here's a summary. The idea that you can model computability by continuity can be extended to all of constructive type theory using Per Martin-Löf's constructive type theory, which implements computability. And then, when you do that, the type theoretic constructions become homotopy invariant structures and theorems in the system. Constructive proofs then yield programs for automatically calculating homotopy invariance inside this computational proof system. The calculations of the homotopy groups of the spheres were a proof of concept for the system. The system itself still remains experimental, but we're making progress year by year. And now I want to step back a little bit and point out that classical foundations of mathematics using sets, like as is used in the lean proof assistant, are a subsystem of this constructive foundation using homotopy groups and homotopy types, because a set is just a discrete homotopy type. And the classical foundations are a special case of this constructive system. So that promises a great deal of potential for future research. So that's where we're headed. And I'll give the last word to Gottlieb Frege. We talked yesterday quite a bit in several of the talks about spatial reasoning and the difference between spatial and maybe algebraic reasoning, and the fact that we need a formal language to do spatial reasoning. Now, I've just told you about this implementation of homotopy theory, which is nothing if not spatial, into the formal system computational, logical, combinatorial system of type theory. And already Frege had this idea in the preface to his Begriffsschrift, the founding document of modern logic. He says, I'm convinced that my Begriffsschrift will find successful application wherever particular value is placed on the rigor of proofs, as in the foundations of the differential and integral calculus. It seems to me that it would be even easier to extend the domain of this formal language to geometry. Only a few more symbols would be needed to be added for the intuitive relations occurring there. In this way, one would obtain a kind of analysis situs. I think that's exactly what we've got. So, thanks very much. Yeah?
So, it appears that this is a tough computation. Computing the homotopy groups of spheres seems to be a hard computation.
Very much, yeah.
Are there any decompositions known in terms of what kind of finite groups might appear?
Oh, yeah, well, there are lots of decompositions for there's the structure theorem for abelian groups, and you can decompose a abelian group into a finitely presented group, into some torsion groups, and then a free component, and those are the factors in the finite presentation that the Serre-finiteness theorem produces. It gives you a coefficient for the free summand, and then it gives you the finite presentations of the other summands. So yeah, that's what it spits out computationally. It spits out the decomposition. Good question, yeah.
Maybe I can ask a question.
Yeah.
In this theory, are there concept of distance and orientation?
Concept of distance.
Yeah.
There's no metric structure on the homotopy types, right? So that would be an additional thing that you'd have to impose, right? But that's not to say it can't be done, and there is a kind of a smooth homotopy theory of differentiable manifolds, something like that, where the deformations now have to be maybe smooth or at least differentiable or something like that. And that can be introduced, and there is a theory for that. There's a very, I think, promising area that's being pursued right now, which is a extension of just the bare homotopy theory is this continuous deformation without any smooth or differentiable structure. But differential geometry, of course, pursues an idea of smooth deformations. And there's a theory of what's called synthetic differential geometry, which puts that into the setting of homotopy theory. The whole procedure that we are pursuing here is just the jargon that we're using is a synthetic implementation as opposed to an analytic one. So the differentiable structure is put in axiomatically, and then one reasons synthetically about these structures using type theory rather than analytically using maybe analytic or complex or real valued functions. So that's the approach. Yeah. Yeah.
The HoTT theory, that's more specific for calculating the fundamental rule for homotopy, right? So it can be used to calculate other properties. For instance, can you use that to study the homology group?
I can't quite get it. Maybe I give you the microphone or you have to speak up.
So I'm saying that HoTT
Yes.
is more specific for calculating the homotopy group, right? Can be calculated some other information. So for instance, can it be used to calculate like a homology group, which are much easier to
Yeah.
study the problem?
Yeah, so the reason we took the homotopy groups of the spheres as a test is because it's a classical known hard problem. But you can do lots of other things too. You can do cohomology, for example, by putting in some groups and then homing in to the cohomology, homing in to the like Eilenberg-MacLane spaces or some classifying groups, and then you hom into them to compute the cohomology. There's a homology theory using cellular decompositions of spaces, and you can compute homology groups as well. So there's definitely work on that too. So, yep. I mean, there's also the Serre spectral sequence has been done for homology and so on. So, yeah.
Maybe I can
Good,
ask
sure.
a question.
Yeah.
Do you define similarity?
Similarities.
You define identity as same, but if similarity is
I'm not sure. I mean, homotopy equivalence is a kind of similarity, or being related by a homotopy is a kind of similarity. But do you mean a specific notion of similarity, or?
means what the popular used in network.
Oh, I don't know what that is. I freely admit I don't know anything about this subject. So, but I'd be happy to learn. Maybe similarity would be something useful that I should know about. Okay. Yeah. Okay. Thank you very much. Here are some references. I'll make the slides available.
Can you show again the slide with the link?
Which one?
Previous one.
Is that what you want? Okay. Homotopytypetheory.org, yeah. Hashtag. Shall I stop the recording? Shall I stop the recording, or I'll let you do it? Yeah, you do it, yeah. Good.
Thank you very much.
Thanks.